Hello and welcome back to the Designing VMware Infrastructure video training series. In this lesson, we're going to be taking everything that we've discussed so far and bringing it all together. First, I'd like to set the stage for what we're going to do in this lesson, and then throughout the remainder of the lesson, we're going to be working through a fictional scenario to discuss design considerations and design processes. In this lesson, we're going to walk part of the way through a fictional design scenario. Now, I say part of the way because a true, comprehensive, and complete vSphere design requires a tremendous amount of effort and a tremendous amount of information, far more than I can present to you effectively through this medium. So we're going to just take ourselves part of the way through the design scenario, or part of the way through the design process using the scenario that I've created. And we'll use this scenario to reinforce some of the terminology, topics, and techniques that I've shown you throughout the course. I'll start out first by providing some information, a background on the scenario, and then I'll go to a series of questions. If you need to review the information that I provided, well, the beauty of video training is that you can simply rewind it back to the previous section where I'm providing the scenario background and then proceed ahead again into the questions. So with that, let's look at our fictional design scenario. In our scenario, we have a company, the Wired Brain Coffee Company, who is turning up a new data center and has plans to implement VMware vSphere 5 for the first time in this new data center. Now, Wired Brain has existing vendor relationships with partners like Cisco for their Ethernet networking equipment, Brocade for their storage area networking equipment, EMC for their storage platforms, and HP for their servers and compute nodes. Their staff are well versed in this equipment. They've been using it for some time, and they really don't have any desire to change the vendors that they're using. Right now in their current infrastructure, they're running almost exclusively Windows Server 2003 R2, but as part of this new data center, they're going to migrate their applications to Windows Server 2008 R2. They initially plan or need to host 500 VMs, but they want to be sure to include calculations for 15% growth per year over the next 3 years. Based on the information I just provided to you, let's see how well we do with some of these questions. First, can you identify at least one requirement? Pause the video training here if you need to think about this, or feel free to rewind it if you want to look back at the scenario information. If you said that a requirement was that Wired Brain Coffee needed to run 500 VMs, you're right. That is one of the requirements that was found inside that scenario background. Also found as a requirement was Wired Brain's growth requirements, which they specified as 15% growth per year over the next 3 years. Now let's move on to the next question here. Can you, based on the information I provided, identify at least one constraint? Again, feel free to roll the video back to the scenario information if you feel that's necessary. Most of the constraints provided in this scenario thus far are in relationship to their vendor partnerships. I identified in the scenario that Wired Brain Coffee has a number of existing vendor relationships and do not wish to change those vendor relationships. Those could be considered design constraints in that they are constraining the design. Wired Brain says we only want to use our existing and established vendors as we move into this new data center design with VMware vSphere 5. Now let's take a look at the next question. Can we identify, or can you identify from the scenario information, at least one risk? If you recall from the early lessons of this course where we talked about the design factors, that risks sometimes don't present themselves until you do your requirements analysis. When you establish your requirements, and then based on those requirements and the constraints, you can then begin to build out and determine where risks might appear. In this particular case, we do have a risk that is easily identified, and that is that the Wired Brain Coffee staff do not have any previous experience with vSphere. Note that I said that they're implementing vSphere for the first time in this new data center. And what that means is it presents a potential risk in that the existing staff don't know how to operate the vSphere environment. Now, it would be your responsibility as the architect to help mitigate that risk by perhaps including some training as part of the implementation plan, or recommending that they have staff trained before they take ownership of the design. Now, it's early in the process yet, and you only have a limited amount of information, but what sorts of assumptions do you think might be needed based on the information that you've been provided so far? Well, if you said things like recovery point objective, recovery time objective, service level agreements, backup requirements, you name it, there's a whole range of assumptions because I've given you a very limited amount of information. This goes back to the fact that a comprehensive design requires a great deal of information, not just technical information, but also business-related information. What are the kind of applications that Wired Brain Coffee is running? How do those applications interact with the business? How do they impact Wired Brain's bottom line? Those are the kind of things that we need to know, in addition to technology-related questions, in order to really be able to create a design. So it's a bit early yet to have some concrete assumptions, but at least you have an idea that there is additional information. And thinking along those lines, what sort of additional information would you say we need to gather in order to proceed? I've given you some examples already, but what other examples could you think of? Well, some examples might include workload performance characteristics. Are they high IOPS workloads? Are they high bandwidth workloads? Are they high CPU workloads? Are they high RAM utilization workloads? Perhaps some aggregate RAM or CPU values based on an assessment of the current environment? What about storage capacity or storage performance? I mentioned service level agreements, recovery point objective, recovery time objective. What about other DR or BC requirements? Network utilization, network requirements, security. All of these sort of things are additional information that you would need to gather in order to truly build a vSphere design for Wired Brain Coffee. Now let's move on to the next phase of our scenario, where I'm going to give you a bit more information and we're going to look at some more questions. Continuing in our scenario with Wired Brain Coffee, we performed an assessment of the current workloads that they're going to move into their new VMware vSphere 5 implementation in the new data center. They have 500 workloads they want to run, and they're looking for 15% per year for 3 years in terms of growth. Based on the assessment, we determined that the workloads are going to require 468 gigahertz of CPU capacity and 714 gigabytes of RAM. On the storage side, these workloads are going to generate, on average, 57 IOPS, and the read-write split is going to be 62% read, 38% write. Total storage capacity based on the assessment is 48 gigs, and average network utilization for each workload is averaging around 75 megabits per second. Now, based on this information, let's look through a few more examples and calculations of how we can use this to begin to craft a VMware vSphere design for Wired Brain Coffee. So now that I've given you some additional information regarding our design scenario here, let's see how we can use that design scenario information to continue our design process. In this case, we're going to look at compute workloads. Now, I've specified here that we're going to use servers with 16 cores, 2.2 gigahertz per core, 96 gigs of RAM. And how many servers would be required in that case? Well, we know that the logical compute design has pretty much already been given to us. That logical compute design was provided at 468 gigahertz of CPU power, right? And 714 gigabytes of RAM. So using that information, how can we then proceed with calculating what our physical storage design is going to look like? Well, at first glance, you would say, well, I'm just going to take this 468, I'm going to divide that here by 35.2. That 35.2, by the way, is 16 cores times 2.2 gigahertz each. And if you were to walk through that calculation, you'd end up with 13.3 servers, or then you'd round that because we can't have 0.3 servers, to 14 servers required to meet the CPU requirements that were specified in the logical design provided in the scenario information. And if we use that same process for our RAM, then we could say that 714 gigabytes divided by 96 gigabytes per server, that gives us approximately 7.4 servers. And again, we would round that up to 8 because we can't have 0.4 servers. That seems pretty reasonable, but the problem here is that we've overlooked something. Those 16 cores at 2.2 gigahertz would only be able to provide 35.2 gigahertz total capacity if we ran it at 100% utilization. And, well, in most cases, when we run something at 100% utilization, our response times are not going to be what we need. In addition, what we've specified here, our total aggregate CPU capacity, may not account for specific peaks in workloads, perhaps quarter-end peaks or month-end peaks as Wired Brain goes through processing all of their sales reports. So we'll need to throttle that back a little bit. And instead, what we need to be looking at is not 468 divided by 35.2, but rather, let's look at 80% of each platform's capacity. And that would be 28.16. That's obtained by taking 35.2 and looking at 80% of that. If we use these numbers, then we come out at 16.6 servers, and we would round that to 17 hosts. Similarly, if we look at 80% memory utilization, we won't be dividing by 96. Instead, we'll be dividing by 76.8, which gives us approximately 9.3 hosts. And we would, of course, round that up to 10 hosts to satisfy our requirements. So as you can see then, looking at 80% utilization, and based on the logical compute information on aggregate CPU capacity and aggregate RAM capacity, we would need 17 servers, 16 core, 2.2 gigahertz, in order to meet the CPU requirements, but we would only need 10 servers at 96 gigs of RAM to meet the RAM requirements. With this information in mind, what does that tell us about Wired Brain Coffee's workloads? Are their workloads more CPU intensive or more RAM intensive? Well, looking at the numbers, we need more servers to satisfy the CPU requirements than we do to satisfy the RAM requirements. That means their workloads are more CPU intensive. With that in mind, then, what are some of the design considerations or design impacts that come from running CPU intensive workloads? Are there other considerations that we need to include? Perhaps we should be looking at lower target VM to core ratios than perhaps if the workloads were less CPU intensive. Remember that our target VM to core workloads, or VM to core ratios, will indicate how many VMs will share a single CPU core. In this particular case, if we look at the total number of workloads, we know that we have 500 workloads. And we look at the total number of cores, which, if my math is correct, we have 272 cores. Our target VM to core ratio is already at 1.8. So we already have a pretty low target VM to core ratio, and perhaps that'll be sufficient. As we add workloads to here, we'll have to watch whether these workloads are CPU intensive as well, and if that's the case, we may have to grow the environment more quickly than we would otherwise. Adding less CPU intensive workloads to this environment may be easier to do. If we had found that the workloads were more RAM intensive, then we would have to take into considerations on whether or not we were going to use memory overcommit. Were we going to actually allocate more than 96 gigs of RAM per host to VMs running on that host and allow vSphere's underlying memory management technologies like idle page reclamation and transparent page sharing to allow us to manage that overcommitment? If an environment is RAM intensive, it might not be the best approach to use memory overcommitment. If, however, the environment is not RAM intensive, then you might be able to get away with overcommitting RAM. Or in this case, we might be able to reduce the amount of RAM in our servers, since we know that we have to have 17 servers to handle the CPU capacity anyway. We might be able to reduce the amount of RAM in the servers and therefore save a little bit of money on the overall project. So those are some questions and calculations regarding compute workloads. Let's look at some more. Now that we've discussed the calculation of the compute environment by taking the values from the scenario that created or comprised our logical compute design, and then using those values to calculate a physical compute design, I'd like to turn our attention to the storage design. I gave you some information around the logical storage design already. I gave you a total number of IOPS required per VM. That number was 57. So we have 57 IOPS per VM with a total capacity per VM of 48 gigabytes. Now I'll start with the capacity here. This is easy to calculate. If you take 48, you multiply that times 500, then you come up with a total storage capacity requirement of 24 terabytes. We'll come back to that in a moment, but for now, your total storage capacity is going to be 24 terabytes. That's 48 gigabytes per VM at 500 VMs, 24 terabytes. Now, coming back to calculations. So we know, first of all, what our total number of terabytes is. Now we need to figure out what our total number of IOPS are, and then we can go about figuring out how many disks we're going to need to support that, both for IOPS and for capacity. Fortunately, the IOPS is not as straightforward as the capacity. We do have to do a different calculation here, and we also have to consider which RAID level we're going to use. Now, recall that we also had to look at the read-write split. So in this case, we're looking at a read-write split of 62% read, 38% write. And so if we assume a RAID 5 backend, then we can begin to calculate what our IOPS load is going to be on the actual array itself. So we'll do that by first taking 62% of the IOPS, which in this case is 35.34. We'll add that with the 38%, which are writes, and then we multiply that number by the RAID write penalty with RAID 5 in a 4+1 set. That is a write penalty of 4, and that gives us a total IOPS load of approximately 122 per VM. If we then extrapolate that out at 500 VMs, then we run up with a IOPS workload of approximately 61,000 IOPS. And at 175 IOPS per drive, and I got that because we specified a 15K fiber channel drive, and it's reasonably accepted that a 15K fiber channel drive can provide about 175 IOPS at a reasonable latency. Then we end up with approximately 348 drives needed to support 57 IOPS per VM at 500 VMs. On the capacity side, and in a 4+1 RAID 5 set, then we need 5 disks to give us 2.4 terabytes at 600 gigabytes each. And we need 10 of those 5 disk sets, so that gives us a total of 50 drives to support that capacity. So 348 drives to support IOPS, 50 drives to support capacity. So looking at that information then, are these workloads more IOPS intensive or capacity intensive? Notice that the number of disks required is significantly higher. But that doesn't really tell us whether they're IOPS intensive or disk intensive. This is more a function of the fact that I can provide 175 IOPS out of a spinning disk like a 600 gig fiber channel drive, but I can provide 600 gigabytes. This is a reflection of the fact that disks have grown in capacity much more quickly than they've been able to provide in terms of IOPS. So what if we were to change this around a little bit? Remember that we have to, as an architect, we have to understand design impact. So what if we change this around again? What if we say, instead of using RAID 5, we're going to use a 2+2 RAID 10 set, which has a RAID penalty, a RAID write penalty of only 2. So if we go back through our calculations again, 35.34 is the 68 or the 62% read, then 21.66 are the writes with a write penalty of 2. That gives us an overall IOPS load of approximately 79. Extrapolated out at 500 VMs, we are just over 39,000 IOPS. And at 175 IOPS per drive, that gives us approximately 224 drives needed from an IOPS perspective. Changing that over here, we would need 4 drives to give us 1.2 terabytes. And in order to get to the 24 terabytes that we need, we would end up needing 20 of those groups, so a total of 80 disks. So by simply changing it to RAID 10, we reduce the number of overall disks required to support IOPS by 1/3, but only increase the number of disks required for capacity by half, a little over half actually. Half would be 75, we're at 80 drives. And now we can begin to look at, are there other things that we can or should do here to further optimize this design based on what we know? Would it be of any benefit here, and we continue to use the what if scenario to explore design impact, would it be of any benefit here to employ some sort of deduplication technology? Well, not really, because we're not bound by having to add disks for capacity. We're bound by having to add disks for IOPS. And again, this is a reflection more of the fact that disks can provide far more storage space than they can IOPS, with the exception of flash drives. So perhaps a better technology to explore here would be the use of flash in some mechanism, some form, whether that be flash as cache to help absorb some of the reads and writes, or whether that be flash as a storage tier. If you were going to use flash as a storage tier, there's another piece of information we don't have here, and that piece of information is called the skew. In other words, what percentage of the data generates the most writes, and that would help us determine how much flash would be necessary. General rule of thumb based on information gathered from real-world deployments shows that less than 10% flash in a tier would generally help tremendously. We'd have to go through some more detailed calculations, but you get the idea here that perhaps if we were to add just a few flash drives, we could dramatically reduce the number of spinning drives required, and then we could look at an analysis of the cost. How much did it cost to add those flash drives? How much did it cost to license any software necessary to do any tiering or data analysis versus how much money did we save with not having to buy additional drives, and how much money will we save, if any, looking at operational costs, power, cooling, that sort of thing. The same can be said for looking at RAID 5 versus RAID 10. Yes, we have to buy more drives, but we can buy fewer drives because of capacity. All of these things are things we have to take into consideration as we look at this. This is a reminder of the need that we have to look at this holistically, so we can't consider things only from the perspective of IOPS. So we can't look only at the fact that each VM generates 57 IOPS, and we can't look at the fact that each VM generates 48 or needs 48 gigs. These two pieces are interlinked, and that's part of what we talked about, needing to maintain a holistic view of not just one aspect of the design, but every aspect of the design as you move forward, because a change in one area will invariably have an effect in another area, and we need to understand that effect and be able to account for it. Now that we've looked at some storage-specific discussions, let's turn our view to the network. I'd like for us to now turn our attention to the networking side of our scenario. Based on the information that we've seen thus far in calculating through our compute nodes and calculating through our storage, we figured that we would need about 17 ESXi hosts. Those 17 hosts are 16 core systems at 2.2 gigahertz and 96 gigs of RAM. Now, based on that, can we calculate about how many VMs we're going to be running per host? Well, that's fairly straightforward. We're just going to take our number of VMs, which we know to be 500 based on the scenario information. We divide that by 17, and we ran up at about 29.4 VMs per host. Since we can't have an odd number of VMs per host, we'll round that up to 30. So 30 VMs per host, and that is in line with our calculated VM to core ratio earlier of about 1.8 VMs per core. This was our discussion when we were looking at the compute nodes about whether these were CPU intensive or RAM intensive workloads. Now, based on that number of about 30 VMs per host, can we figure out how much network throughput those VMs are going to generate? We can indeed. If we look at 30 VMs and each VM generating about 75 megabits per second, then our total is 2250 megabits per second, or 2.25 gigabits per second. So we're looking at each host generating about 2.25 gigabits per second based on the assessment that we did and how much network throughput the VMs were generating. Now, based on that, how many NICs do we need to allocate to handle our VM network traffic? Well, if we assume we're going to use 1 gigabit NICs, then we could get by with just over 2 NICs, but that's assuming that each NIC is capable of running at 100% utilization. And the reality is that full duplex Ethernet typically will run at about 80% utilization. So if we look at about 800 megabits per link, then we could do 3 links, and that would get us 2.4 gigabits per second. But there's a problem here, because with only 3 NICs, how are we going to provide network redundancy? Are we going to take a single vSwitch and take all 3 NICs for VM traffic and connect it to a single physical switch? Well, then we've got a single point of failure. What if that single physical switch fails? What we really need is to be able to take the links for our VM network traffic and split them across 2 physical switches, like this. That means even though we could get by from a network bandwidth perspective with only 3 NICs, the recommended configuration would be to set aside 4 NICs for VM network traffic. Now, that's in addition to any NICs that we might allocate for vMotion, any NICs we might allocate for fault tolerance, any NICs we might allocate for management, and any NICs we might be using for storage if we are indeed using Ethernet-based storage such as iSCSI or NFS. Now, why is that important? Well, it's important for a number of reasons. One, it's going to drive how many physical switches you're going to need and what kind of physical switches you're going to need. So we know at 4 links per host and 17 hosts, then that gives us a total of 68 ports that we're going to need. When we look at how we do this, okay, between 17 hosts, we need 68 ports. So how many physical switches is that going to be? Well, if we use 48 port switches, that means that we're going to have 34 links per switch split across 2 switches, which means a 48 port switch would suffice and would leave us some room for uplinks because we potentially haven't calculated any sort of 10 gig uplinks or using some trunks to go up from there. It'll also tell us how many NICs need to be in our compute nodes. So this will drive the selection of our compute nodes. We need to make sure that we select compute nodes that are capable of supporting at least 4 NICs. Now, there's a variety of other considerations that we haven't taken into account here. We haven't taken into account, for example, security requirements. Do any of these VMs need to run in a different security zone or a different trust zone than some of the others? That would drive more NICs or a different sort of network configuration. We haven't discussed whether or not we should use 10 gigabit Ethernet here and what that might look like. So there's a lot of other considerations, but at least this gives you an idea of some of the calculations you can go through that will at least put you in the ballpark of where you need to be as you select the network design based on the information that you have in calculating the design factors. Now, I'd love to take you through even more design scenarios, but we're going to have to stop here for now. Hopefully, these last few sections that I've shown you have given you some food for thought and given you some valuable information on how you can pull all of the various pieces together from this course and use them in designing VMware vSphere environments. And that's it for walking through our fictional design scenario. I would have loved to continue to explore all the various relationships and dependencies and calculations that are involved in creating a comprehensive VMware vSphere design, but as I mentioned earlier, that requires a great deal of information and a great deal of time, and well, unfortunately, I'm out of time. I hope, though, that what I've been able to share with you during this fictional design scenario has really helped to reinforce all the concepts, the terminology, the ideas, the techniques, the tools, and the procedures that I've described and covered to you throughout this course. So what we covered in this lesson is, first, we set the stage for the fictional design scenario by talking about what we were going to do and the information that was provided to us. And then we worked through the scenario to give you a real life, or as real as we can with a fictional design scenario, example of some of the calculations that are involved, some of the explorations that are involved, the relationships, the dependencies, all with an eye towards reinforcing the holistic view of the design, of being able to look at the design with the big picture in mind, and remembering that all these pieces are intricately interrelated with one another, and you can't consider any one piece on its own. That's it for this lesson. Thanks for watching.